Awesome. So let's do one example. I left some extra space. And it should be very familiar because this was on the Chapter 4 test. It's where the kid on the sled has some friction. We'll displace him forward 5 meters. Oh, maybe you didn't have the same form. So, okay, we're pulling with 100 newtons at 53 degrees, 53.1030, something like that. You know the one, 53. And it's a 200 newton sled, or 20 kilograms. Okay, find the work done on the box. Okay, so I wanted to show this one to show we're going to end up doing exactly the same procedure. Okay, but energy, once you get used to it, energy is like a better way to think about it. So displacement is only forward 5 meters. The cosine of 53 degrees is much steeper than this. So that's going to be 60 newtons forward. I have a force of friction though, so I do have to go through all my rigmarole. Okay. But I know right away. Okay, so yeah, from chapter 4, I can say the sum of the forces in the y direction equals 0. I don't get, uh, I don't come off of that plane, the surface. I only move horizontally. But from an energy consideration, all I need to know is that there's no displacement in the y direction. Any energy, there's no kinetic energy change, because any force times 0 delta y is 0. I don't need to think about those forces. Okay, I only need to know what the force of friction is, because that's the one that goes backwards from the displacement. So I'm going to get some positive work out of this one, and we get some negative work. Yeah, you can take away, right? And you should, so work done by forces can be positive or negative, just like money. Money can go into your account, positive, in the black. Money can come out of your account, negative, in the red. Okay? When you do negative work, you're taking away some kinetic energy. You're trying to slow it down. Now, maybe it doesn't actually slow down if something else has more positive work. Okay? So, like the work done by friction is going to be the negative friction force, negative direction. You can also think, okay, from the actual displacement that happens forward, the angle to the friction force is 180 degrees. Okay? And the cosine of 180 is negative 1. Oh, wait, let me flip back to that. No, okay. I should have said, whoops. Okay, come on, way down there. Okay. I need like a scroll button. A better way to write this, F dot X, whoops, yep, net force times displacement, is if I just take the magnitude of the force times magnitude of the displacement times cosine, always cosine, of the angle between them. That's a simpler way to write this vector stuff. And that's always equal to the work done by that force. Okay. That's really the only feature of what we call the dot product. Yes, there's an X product, there's a cross product, but we don't need that right now. Okay, so there are actually different ways to multiply, especially when it comes to vectors. Okay, so we always want the cosine of the angle between those two vectors. Still need that, great. So when we go back to our problem, okay, friction force times displacement. Friction, like always, we have 200 pointed down, but we have an 80 up. So the normal force is only 180. And then the friction force is 0.2, isn't it? Yeah. So the force of friction is 36 newtons backwards. Oh, I did this wrong, fifth hour. Okay, so you got 60 forward and 36 back, and we could dive into kinematic stuff. But what you can also do is just, okay, distance is displacement, or distance is plus 5 displacement. Okay, so you can say, here's my work done by the tension. 60 times 5, it's plus 300 joules. And here's my work done by friction, and it's minus 180 joules. Okay, so my total work done, and in an energy question, maybe that's it, is 120 joules. That's the work done on the box. If I wanted, I could set that equal to 1/2 mv squared. Half of m is just 10. So I can get my final velocity is the square root of 12, or 2 root 3 meters per second. Okay. Did you have that form in the test? Remember that one? So it actually, I didn't have to break down and do acceleration or final velocity or equation 3. Equation 3 was built in there. So, and that is the answer. I've just got an m over 2 built into there. Okay, sometimes we just want the energy, sometimes we'll use it to solve something. Okay, any questions? Okay. So when you get used to energy, it actually makes these problems much simpler. Again, the homework problems, they'll be a little more complicated to make you think. You have lots of time tomorrow to work on them. Hopefully I can show some new tricks. Right, but so now we're aggressively taking the stance of we don't need to know the time. We don't need to know how much time it takes to get from here to there. We're just going to solve. We got forces, we got our displacement, our motion. We can get final velocity if we really want. And that's it. Okay? So there's actually less things to solve for.